Hello everyone, welcome to my YouTube channel. Today we are going to discuss about surface to volume ratio. In order to understand the basic concepts, you can also see my previous video, which speaks about how exactly the particles are changing from bulk to the nanostructure and how the surface increasing. The similar stuff is explanation here, so a few extra points are added. So one of the most fundamental differences between the nanomaterials and the larger nanoscale materials is that the nanoscale materials has got extraordinary ratio of surface to volume ratio, right? So surface is becoming more and more and volume is getting more and more, less and less when I'm reducing the bulk structure to the nanostructure. So for any work, any activity, what we need from the materials is the surface. Like the more the surface, more the applications. And in nanostructures, that is the beauty. We have a lot of surface atoms compared to the inner atoms. That's why the surface to volume ratio is high. So this is giving us a lot of surface to have the activity. That's why within one box, so much box, I can have billions, tens of billions of nanoparticles. So tens of billions of nanoparticles means tens of billions of so much amount of surface. So surface is more, so the activity among these particular structures will be more. So this inverted ratio and its effects on nanomaterial properties is a key feature for nanoscience and nanotechnology. That's what makes nanotechnology so cool. So for these reasons, the nanomaterial's shape is of great interest because various shapes will produce distinct surface to volume ratios and therefore different properties. For example, imagine I have synthesized the nanoparticles which is a spherical shape of 80 nanometer diameter. And the same thing I am going for the hexagonal or the simple as square nanoparticles whose dimensions is around, width is also 80 nanometer. Now can I expect the same property from both? The answer is absolutely no. Even though the size is same, the shapes are different. The spherical has got its own formula, the square has got its own formula. So when you introduce these values 80 nanometer as the surface area, then you get different values, right? Different surface to volume ratio. Once you get this particular surface to volume ratio, we cannot expect the same property what we are getting it from the spherical. For example, I use silver nanoparticles. Imagine I am getting the particular anti-corrosion property for this so and so. That's anti-corrosion property I cannot get for the square or pentagonal or just a cube structures. The reason is very simple. As the surface morphology changes, the surface area changes. As the surface area changes, surface energy changes. As the surface energy changes, definitely its activity changes. It means the activity changes, its properties changes. It means the properties changes, your application change. As simple as that. So the expressions that follow that can be used to calculate the surface to volume ratios in nanomaterials with different shapes and also to illustrate effects of their diversity. So now sphere of radius, we can call it as R. So this is typically the shape of the nanoparticles which are used in many applications. In some cases we can take it as surface energy or surface area is given by the 4 pi r square, whereas volume is given by 4 pi 3 pi r cube. These are the standard formulas. Now I need to add surface to volume ratio. So surface will go for numerator, denominator will be 4. So 4 and 4 gets cancelled, right? That we will see later. Okay, so this is again we discussed. So from macro or a bulk to the microparticles to the nanoparticles. As we are reducing, the surface is becoming more, the volume is reducing, that's why the surface to volume ratio is high. So during this terminology, in this process, what happens? The quantum effects come into picture because more the surface atoms, lesser the inner atoms. So increasing dominance of the quantum effects. Once there is a dominance of the quantum effects, obviously dominance of surface of a particle over that of those interior. So high surface area is nothing but a key for the catalyst to the medicine. So we are having surface atoms to the inner atoms. So here this is the proof that as we are keep on reducing the structure to the nano, we are getting more surface area. So we are having 18 atoms, external atoms here, red one, blue one are inner atoms, 18 by 12 is 1.5. So external atoms are how much? Surface atoms 14, and here the inner atoms 6. So got 2.3. So next we are having 10 surface atoms and 2 inner atoms. The ratio is 5. So as the size is decreasing, we are getting more number of the external system comparatively to inside. It's not like more number of atoms. Obviously more number of atoms are here only, but compared to the inner atoms we are getting more. So where surface to volume ratio is more. So the same thing goes for the 0 dimensional, 1 dimensional, 2 dimensional, 3 dimensional materials, where we can use the particular things, and that's how the things will work. Okay. Okay, so basics to geometry is there, that is 0 dimensional, 1 dimensional and 2 dimensional. Basic geometry 0 dimensional, we are having quantum dots or something in the nanoparticles. With the help of that we can have billions or millions of quantum dots. I can put it into one sheet of a paper, that will be my thick film, but here diameter will be in nano size, so nano composite. Now with the help of thick film I am preparing one bulk material, that will be bulk nano composites. Same thing goes for the carbon nanotubes, nanowires, rods and so on. Next we are on surfaces, 2 dimensional. With the help of n number of films you can get the thin film on substrate, and then bulk nano composites out of it. The same thing. So here surface to volume ratio for a sphere, cube and cylindrical as a function of critical dimensions. So you are having the blue line as sphere, cylindrical as red, cube is green color. So nanoscale materials have extremely high surface to volume ratio as compared to the large scale. See, surface to volume ratio in reversible, and we are having critical dimensions. So as the nanoparticle size is keep on going, as the ratio is keep on increasing. See, from 100 whatever the surface to volume ratio was there, maybe 0.1 or 0.2 or something like that. As you keep on increasing 60 nanometer, it is all the structures, not only the cylindrical, not only the cube, not only the sphere, everything is, every shape has got its own this thing. And when the things are changing less than the 20 nanometer, the surface to volume ratio is increasing like anything. See, it's almost 2 times, 6 times, 600% increment. So that's how the more 600% increment means 600 times better in activity. That means 600 times better applications. That's the beauty. So the same example what I gave you previously, you take this particular one area, 1 meter square cube, the total area will be 6 meter square. Why? Because it has got 6 faces. Now if I keep on dividing it, and I am dividing it to 2 times, I am dividing it into 3 times, I am dividing it to n number of times. So when I am dividing this 1 meter box into around 10,000 different these things, so obviously I will be getting 100 nanometer as one block. So once I reach 100 nanometer, the surface area if you calculate, it is 2.5 acres, but the volume is fit into just 1 meter square. Understanding? So much area. So when I cut here, obviously inside part will be explored, that is extra surface. Like that we are getting the areas. Like that, when the whole bulk I make, now this bulk which 1 meter, which is bulk material, and this will be called as a bulk nanomaterial. So which will have more surface area? Here just 6 meter square, here it will be 2.5 acres. So now you are understanding why the nanotechnology is so important. That's why, because of the surface to volume ratio only, the nanoparticles has got significant applications. In 1 meter square box or 6 meter square area or 1 meter square box, I can fit 2.5 acres of surfaces. Understand? Surface. So this is how the, if you want to say with respect to the formulas, you take the 2 meter which is bulk meter sphere and 2 nanometer sphere. Okay, now compare, let's compare how much difference is there. Surface area, we are having a formula 4 pi r square, volume we are having 4 by 3 pi r cube. Now if I am using this surface to volume ratio, then obviously the things will cancel out, many things will cancel out. So here total, if I am adding, so r is nothing but what here is 2 meter. So when I am adding 2 meter here, so I am using this thing, okay, and I'm getting so much. Surface area will be around 3 per meter, right? So it's in the reverse, and the same thing goes for the 2 nanometer. When I'm using the 10 nanometer here, it keeps on going. That's 3 divided by 1 nanometer will be in the end. That has to be multiplied, and that will be converted into meter, because the IST standard this thing. So now 3 into, now the denominator 10 to the power minus 9. Now 1 nanometer means what? 10 to the power minus 9 meter. So I'm converting nanometer into 10 to the power minus 9 meter. That's it. So once the denominator goes to the numerator, the sign changes. This negative sign will be changed to the positive sign. So 3 into 10 to the power 9 per meter. So by reducing from 2 meter sphere to the 2 nanometer sphere, I can increase the surface to volume ratio by 10 to the 9 times, that is billion times. So by reducing the size of the sphere from 1 meter to the 1 nanometer or 2 meter to the 2 nanometer, the surface area to the volume ratio increases by a factor of 10 into 9, that is nothing, 10 to the power 9, that is nothing but billion times. Understanding? So much. If it is 1 acre is there, 9 billion, 10 billion, 1 acre is there, 1 billion acre of surface area. 1 meter, 1 billionth of meter. Okay, surface area. That's how it works. So sometimes something to be considered here. Suppose we make a spherical gold nanoparticles that contain enough volume of 10,000 unit cells, which is equivalent to around 0.55 nanometer diameter. Note that this particles approximately 1/3 of the unit cell that are one side touching the surface. So like this. So now since the gold forms into the cubes, now if you are going for the spherical gold to the cubes, then one could easily see how nanoparticles could be cubic. But how spherical and still have cubic unit cells? Because the answer is that it is not possible. So either the outside of the sphere has to look like this outside, or the atoms have to change positions at the surface. So if the atoms change the positions, what happens? How deep into the nanoparticles does this go? So it turns out that in some systems what happens, you can make a material that is normally crystalline into an amorphous materials, or even change the crystal structure entirely. Of course, the properties of the material change dramatically if this happens. So here we are saying, if the particles are sphere or in cubic or any shape, every shape gets a different surface area, and that surface area will give you different property, and that different property will lead you different applications. That's why the surface plays a very important role. So surface composition also plays a very important role. For a single atom, for a material, the arrangement of the atoms at the surface can be very different than the arrangement of the atoms in the bulk. At the nanoscale, it will be very important. Okay, that will be totally different for the your bulk properties. For materials with more than one atom, not only can the arrangements of the atoms at the surface be different, but the composition can also be different. For example, say for example you are having the compound AB. So overall we have equal amounts of A and B, like 50% A is there, 50% B is there. But it is possible that at the surface we have much more A than B. Imagine there is a alloy, but A and B, which is composition of A and B. Now A on the surface has got more. So but it is possible at the surface we have much more A than B. So in non-nanomaterials what happens? This surface enhancement of A does not affect the bulk properties. But since the amount of the material at the surface is minuscule, because minuscule, that is minimum. See, A and B at bulk structure, whatever is having maximum outside, it doesn't matter, because in bulk. But in nanomaterials, this surface enhancement not only affects the surface properties, but it also affects the bulk properties, since there is much more B in the bulk than A. Okay, so since the amount of the material at the surface is not minuscule, so that's why in nanoscale the properties do change. The factors that govern the properties at nanoscales are surface to volume ratio and as well as shape. Okay, that's what we discuss in detail in this topic. Next, so because of the surface area, the surface energy changes, Then because of this, the thermodynamics properties changes. Because of this, electronic structure, that is spatial confinement, changes. We are having 0-dimensional confinement, 1-dimensional confinement, 2-dimensional confinement, and 3-dimensional confinement. 3-dimensional, whereas 0-dimensional means all the 3 dimensions electrons are not free to move. 1-dimension, only 1-dimension electron is free to move. 2-dimension electron free to move. 3-dimension nanometer will have all the 3-dimension electron are free to move. So surface interaction in the end, right? So these all are the properties which govern at nano factors which govern at nanoscale. So next topic is confinement. Just now I told you, 0-dimension, 1-dimension, 2-dimension, and 3-dimensional system that we will study in the next class.